Welcome to another episode of Mr. Avila Physics. Today we're going to be talking about electric potential. Now, the first thing we have to do is define electric potential energy. Now, in order to be able to apply the conservation of energy theorem, we need to define potential energy. Now, in previous chapters, we've defined potential energy as the negative of the work done by the conservative force as an object moves from point A to point B. Okay? When we discussed gravitational potential energy, we defined potential energy as the negative of the work done by gravity as an object moves from point A to point B. So here we have the change in potential energy is equal to the negative of the work done by the force. In order to define electric potential energy, right, we see a charge move from a certain point A to another point B, and we define it as the negative of the work done by the electric force as the charge moves from point A to point B. So, in other words, work would be equal to negative F times D. Okay? Let's see if we can visualize this better. So let's look at two equally charged parallel plates. Right? One side of the parallel plate is positively charged, the other side is negatively charged. Right? We assume their separation is small compared to their width and height, so that we can assume constant electric field between the plates. Now let's take a tiny positive charge and place it at point A, right about here. So we're going to take a positive charge, place it here. As soon as this charge is placed here, right, it's going to feel a force due to the electric field. Now the force that this charge is going to feel is going to be towards the right, right? The charge is positive. This plate is positively charged, so it's going to feel a repulsion force, and the charge is going to move to the right towards B. As this happens, the charge is going to accelerate. Therefore, it's going to be gaining kinetic energy, which means that it's going to be losing potential energy. So this tells me that the potential energy at point A is greater than the potential energy at point B, because that's the only way that the conservation of energy theorem can hold true. As you gain kinetic energy, you would lose potential energy. So there is high potential energy at point A and low potential energy at point B. So if I want to calculate the change in potential energy, first I have to calculate the work. So the work done by the electric field to move the charge is work is equal to force times distance. Force is equal to Q times E. So that means that work is equal to Q times E times D. Right? Which means that the change in potential energy will be equal to the negative of the work done, which would be negative QED. Now, one thing we do have to keep in mind is that, okay, this force right here, this is the electric force. Now, the electric force, we can calculate it as K Q1 Q2 over R squared. And then if we multiply it times the distance, which we can also say it's R, I can say that the work done could also be equal to K Q Q over R. Okay? And the change of potential energy would be the negative of this value right here. Okay? All right. Now that we defined potential energy, we can define potential. There is a tiny difference between potential energy and potential. So electric potential is defined as the electric potential energy per unit charge. So simply said, electric potential V is equal to potential energy per unit charge. So this means that this is going to be equal to K Q Q over R over Q. So this is going to be equal to K Q over R. Okay. Oh, so okay, just keep in mind that tiny difference. Potential energy is the negative of the work done by a conservative force, while potential is just the potential energy per unit charge. So if we look back to our example of the parallel plates, we can see here that at point A, since there is high potential energy, there's also high potential. And at point B, there's low potential energy, so there will also be low potential. All right, so we cannot, it's very hard to measure potential by itself, right? We need to be able to measure the change or the difference in potential, right? Potential by itself is very hard to measure. So when the electric force does positive work on a charge, the kinetic energy increases and the potential energy decreases, which means that the difference in potential energy is going to be equal to the negative of the work done. Okay? So potential difference can be defined as change in potential is potential at B minus potential at A, which is potential energy at B minus potential energy at A per unit charge, which is the negative of the work done per unit charge. However, if we want to define the electric potential at a given point, we can look at the difference if we make one of these points 0 by making the distance between them very, very large. We're going to talk about this in the next couple of slides. So, electric potential, like the electric field, does not depend on our test charge, as we saw from our formula, right? V is equal to KQ over R. So, what potential depends on the other charges that create the field, right? So, other charges create a field. You place a tiny test charge in that field, and that tiny test charge feels a difference in potential or a change in potential energy. But the potential itself is always there, regardless of whether you put a tiny charge or not. So if we revisit this example, we can see that, okay, if I place a positive test charge here at point A, there's going to be high potential, and A is going to move from high potential to low potential. If I were to do that with a negative charge, then it'd be the opposite, right? The high potential would be over here at point B if the charge would be negative. Okay, this would be the high potential, and this would be the low potential. So a positively charged object will naturally move from high potential to a low potential, and a negative charge would do the reverse. All right, okay, so you've probably haven't heard potential difference before, but voltage you've probably heard before. Voltage is just another name for potential difference. All right, let's look at some examples, see if we can figure this out. So suppose an electron in a cathode ray tube is accelerated from rest through a potential difference of 5,000 volts, right? Now, this does not mean that the potential here is 0 and the potential here is 5,000. It just means that the difference from point A to point B is 5,000 volts. All right, and the question is, what is the change in electric potential energy for the electron? And B, what is the speed of the electron as a result of this acceleration? Pause the video here, take a couple of minutes and see if we can solve this example. All right, welcome back. So let's look at how our textbook solved this example. So the first question is asking for the change in potential energy. Now we know that voltage or potential is defined as potential energy per unit charge. So if I solve that equation, then I can see that potential energy is equal to Q times V, which gives me this. Okay? This negative sign means that the potential energy decreases. Does that make sense? Yes, because as you move from point A to point B, the electron is speeding up, gaining kinetic energy, which means that it's losing potential energy. Now to solve B, we need to find the velocity of the electron. To find the velocity of the electron, we need to find its kinetic energy. So the loss of potential energy becomes the gain in kinetic energy. So how much potential energy did you lose? Negative 8 times 10 to the negative 16 joules, which means that, the change in kinetic energy is equal to the change in potential energy. So 1/2 mv squared is equal to 8 times 10 to the negative 16 joules. Solve, and we get this velocity right here. All right, hope this video made sense. I want to thank you for watching, and I'll see you next time.